Hello, everyone. So today I want to start with you a new session. This one is a little different. I want to give you some um like topics that are not necessarily associated with one course, but they are helping formulas that you can develop yourself. So I'm going to look at some functions expansions and then, maybe something that would be relevant, and I hope you like it. So let me share the screen with you. Okay. So what do I mean by function expansion? If you haven't yet learned like Taylor's expansion or Maclaurin's expansion, so you are still taking Calc 1, I will introduce it in from a different perspective. Let's assume I have a function. Let's take an easy one, e to the x. But I want to write e to the x as a polynomial. Is that possible? Well, let's see. So the way we are going to approach it, let me tell you something. This is how my late grandfather told me or taught me how to use it. So in fact, this was like I learned that like I don't want to tell you, I don't want you to get panicked, but it's like over 50 years ago. Um, and the way he presented it was so simple that I still remember it till today, but it's so easy. And I think you might have seen it somewhere else. I mean, because he didn't invent it, right? So e to the x, if I want to write it as a polynomial, I'm going to write this polynomial as follows. A term a, which is a constant, plus a term times x, plus a term times x squared, plus a term times x cubed, and so on and so forth till infinity. Okay? If I write it like that, everybody knows that e to the 0 is 1, right? So all what I have to do are these two steps that I will take, over and over until I get a function, or if I until I'm satisfied. I can see the pattern and I can see what will happen even if I take 100 differentiations. So for x equals 0 or at x equals 0, e to the 0, which is 1, would equal a plus b times 0 plus c times 0 squared so plus a bunch of zeros. So I got from here that a equals 1. Then I'm going to take my function and take the derivative of it. So I'm going to say d dx of e to the x, which is still e to the x, equals d dx of that, which is b, plus 2cx plus 3d squared x squared plus till infinity. And again, I'm going to say for a or at x equals 0, the left-hand side is 1, the right-hand side is b. So b equals 1 also. Then I take the derivative another time of e to the x, which is still e to the x, but this time I will get 2c plus 6d x, I'm sorry, plus 6d squared x, right? Oh, why did I do d squared? I'm sorry, plus c, I said, where does the square come from? Plus, if I had a fifth term, so for example, if this was e x to the 4, that would be 4e x cubed, and here I can say plus 12e x squared. Again, x equals 0, then e to the 0 is 1, and the right-hand side is 2c. So c equals 1/2, right? If I divide both sides by 2. One last time. I'm going to take the derivative one last time. I get e to the x. This is 0. I get 6d plus 24e x plus. Again, x equals 0. Left-hand side is 1. Right-hand side is 6d So D equals 1/6. If you repeat it, you will get E would be 1 over 24, F would be 1 over 120, and so on and so forth. And this should remind you of something. I can rewrite, instead of saying 1 over 6, I can say 1 over 3 times 2 times 1. And this is 1 over 2 times 1. And this is 1 over 1. And this is can be, so I can write D. So I can write D equals 1 over 3 factorial. C is 1 over 2 factorial. B is 1 over 1 factorial. And even A is 1 over 0 factorial, which by definition equals 1. So now I can see that e to the x can be easily expanded as 1 over 0 factorial, which is a, plus 1 over 1 factorial x. So when the x is to the power of 1, I divide by 1 factorial. When it's x to the 0, I divide by 0 factorial. If x is 2 square, meaning I divide by 2 factorial, and so on and so forth. And notice that if you take the derivative of that, you will get the same equation again. Because this derivative is 0, the derivative of that is 1 over 1 factorial, which we can rewrite as 1 over 0 factorial. Here, when you take the derivative, the 2 would make the 2 factorial only 1 factorial, and that would be x to the 1. And that's why you see that the derivative of e to the x is e to the x. We already know that. But that's how easy we can find the expansion of e to the x. Let's take another one. Let's take one we all know, which is, for example, sine x, or cosine for that matter. I know that sine x can be written as a plus bx plus cx squared plus dx cubed, and let's do even ex to the 4. I also know sine of 0 is 0, right? So that helps me to say, let x equal 0, the left-hand side is 0, and the right-hand side is a, plus 0 plus 0 plus 0, so a equals 0. Meaning, I don't have a constant term. Okay? Now I'm going to take the derivative. So I get cosine of x equals b plus 2cx plus 3dx squared. This time I'm not writing d squared, plus 4ex cubed plus. Setting x equals 0, I get cosine 0, which is 1, equals b, plus 0 plus 0, so b is 1. Good. Let's take a derivative another time. Derivative of cosine is negative sine x. The derivative of the right-hand side is 2c plus 6dx plus 12ex squared plus. Then if I set x equals 0, sine 0 is 0, and 2c is 0, so c equals 0. And now you can see that every other derivative, I get either a sign or a negative sign. So the a is 0, the c is 0, I expect the e to be 0, the g to be 0, the I to be 0, and every other term, the term that is multiplied by an even power of x, x to the 0, right? Here there is an 0 or 2 or 4 or 6. These would cancel. Think about that and see why, if you know. Anyway, so I can take the derivative one more time. So derivative of sine is cosine, so I get negative cosine of x equals 6d. Setting x equals 0, I get negative 1 equals 6d, so d equals negative 1 over 6. Again, we've seen this before, so I can write this as negative 1 over 3 times 2 times 1, and I can rewrite this as 1 over 1 factorial. Now, I see that very simple. You can see the pattern now. Sine of x doesn't have any second power or even power, I'm sorry, even powers of x, but it has x over 1 factorial minus x cubed over 3 factorial. Who can expect the next term? We are not going to waste your time. What do you think the next term would be? If you said plus, because I alternate the signs, absolutely, because next time you take the derivative of negative cosine, you will get positive sine, which will yield the 0, and then the derivative of positive sine would be positive cosine. So the constant would be positive. Of course, I jump by 2, so this would be x to the 5th over 5 factorial minus x to the 7 over 7 factorial plus x to the 9 plus over 9 factorial and so on and so forth. Very easy, right? Okay. Now, I can do the cosine. Just to save you time, you try it as a personal homework, so to speak, and you will get the cosine. We can do the tan, we can do any function for which we know the derivatives and we know a specific value, right? So I know, for example, I cannot do natural log of x because natural log of 0 is negative infinity. So but I can do natural log of 1 plus x. Yes, I can expand that. You see? So that would be a good introduction to Taylor's series or Maclaurin series. That basically what we are using here. So cosine of x would be 1. Oh, another way to deduce that or to check your work is that after you find it, oh my God, my pen. Okay, you take the derivative of sine, you get cosine. The derivative of x is 1, and 1 over 1 factorial is 1. The derivative of that is negative 3x squared over 3 factorial. The 3 and the 3 cancel, and you get minus x squared over 2 factorial. 5x to the 4 over 5 factorial, the 5 and the 5 cancel, so you get plus x to the 4 over 4 factorial. It's very simple. As you can see, minus x to the 6 over 6 factorial, and so on and so forth. And now I'm going to show you something interesting. We've developed e to the x. I'm going to rewrite it. I'm going to say, notice that this can be written x to the 0 over 0 factorial, right? So e to the x that we just did is 1 plus x. We can say over 0 factorial or not. It doesn't really, the first two, you can simply write them 1 plus x. But just to show the pattern, now, do you see something in common here? For example, the sine of x has the odd powers of x. The cosine has the even power of x. This one has all the power of x. So maybe the first thing you think about is, if I add them, do I get e to the x? We know that sine x plus cosine x doesn't equal e to the x. But why? The problem is with the negative signs. Oh, I'm sorry, this should be minus, right? Minus. Well, let's write it x to the 6 over 6 factorial, and then plus. If I add them, I will get 1, which is this, plus x, which is that. Oops, but this is a negative sign, this is a negative sign. But then I will get this is okay, this is okay, but these two would have negative signs. So like, is there a way that I get plus plus, minus minus, plus plus, minus minus? Is there something that when I raise it to the first power, it stays positive? But when I raise it to the second and third, I get negative. To the fourth and the fifth, I get positive. Do you think, are you thinking what I'm thinking? If you don't get it, that's fine. I mean, because usually you wouldn't think of it. But it's the imaginary number, the square root of -1. I know that I is, so to speak, positive, right? Or I to the 0 is 1. I to the first is I. So both values are positive, so to speak, if we think of positive imaginary. But when I do I square, I get -1. When I do I cube, I get negative I. I to the fourth is 1 again, and I to the fifth is I. I to the sixth is -1 and negative I. Oh my God. So what if I do e to the ix? Notice, meaning every time I see an x, I replace it with ix. You learn how to do functions, right? So I can rewrite this as e to the ix equals 1 plus ix. Notice I'm not gonna divide by 1 minus x squared, because I squared is -1, over 2 factorial minus I x cubed over 3 factorial plus x to the 4 over 4 factorial plus I x to the 5th over 5 factorial minus, and then we go to infinity. That, except for the appearance of the I here for x cube and for the odd numbers, is almost identical, right, to what I have. I could have done something slightly different then, right? I could have said, instead of substituting and finding e to the ix, what if I find sine ix and cosine ix? Would that have helped? Think about it. Or after doing that, I do e to the negative ix. Let's try that. Let's say I'm going to write here e to the negative ix equals 1 minus ix, right? And then I square, if I make x equals negative ix, then negative ix square would be I square x square, which is negative, so that becomes positive x square over 2 factorial. I'm sorry, when I substitute x, no, I should have, if I substitute x as negative ix, yeah, I get negative ix here. Here I get I square x square over 2 factorial. So that's a negative, right? I'm substituting here, not here. And then if I make that cube, it would be I cube is negative I times negative, so plus ix cubed over 3 factorial. And what do I do? The next one, I to the 4th. So if I make that negative I to the 4th power for the next one, which is here, I will get 1. So plus x to the 4 over 4 factorial, and so on and so forth. So what happens? What happens if I say this minus that? Okay? So if I say e to the ix minus e to the negative ix, what should I get? 1 minus 1 are cancelled. Ix minus negative ix is 2ix. This minus that, they cancel each other. And then I have negative 2i negative 2i x cubed over 3 factorial. And then uh, this and that cancel. And here, where I had plus x to the fifth over 5 factorial, so and this would be also plus, would it be plus? No, minus I x to the fifth over 5 factorial. So it means this minus that will give me plus 2i x to the fifth over 5 factorial. Notice what happens here. The first term is the first term multiplied by 2i. The second term is the second term multiplied by 2i. The third term is the third term multiplied by ei. So I can write now sine of x equals e to the ix minus e to the negative ix over 2i. Notice that I could have done something slightly different if instead of dividing, I add. If I said, I'm sorry, I'm using the same paper and I'm probably making it very unprofessional, I know, I'm sorry. If I say e to the ix plus e to the negative ix, what do I get? So if I add these two, 1 plus 1 is 2, these two would cancel. And then I get negative 2x squared over 2 factorial. And then this and that, when I add them, they cancel. And then I get plus 2x to the 4 over 4 factorial. So when I divide by both sides by 2, I get e to the ix plus e to the negative ix over 2 equals 1 minus x squared over 2 factorial plus x to the 4 over 4 factorial minus blah, 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 which is cosine of x. So now we found an expansion for sine of x, which is e to the ix minus e to the negative ix over 2, and an expansion for cosine of x using imaginary numbers. And that, I think I will stop here now. I'm sorry if that seems too complicated. You can, re-look or re-watch it. Watch it. If you watch it again, I think you will, it would make sense to you. And there are, as I said, other functions that you can expand. But next time, I'm going to show you a very nice expansion for polynomial functions or reciprocal of polynomial functions using something that you might have heard before, but its use is so prevalent in math that you wouldn't believe it. It's Pascal triangle that was invented by the French mathematician Blaise Pascal. I'll talk to you about that next time. I hope you would like it. Thanks for your time, and I hope to see you soon.